All right, today what we're going to do is learn how to graph inequalities. So far what we have covered is how we can graph linear equations as well as absolute value equations, and we've done some funky things with those. And so now what we're going to do is apply those same techniques that we did for equations into inequalities. And the first question I'm asking is, how do we sketch a graph of this linear inequality? And then not only sketching the graph, but understanding what it was you just sketched. So I'm asking a few other things, like give an example of an ordered pair that's in the solution set, give an example of an ordered pair that's not in the solution set, and then is an ordered pair on that actual line in the solution set, yes or no. And then we're also going to graph or understand graphs of linear or absolute value inequalities as well. So when we get into graphing inequalities, we need to think back to how did we graph equations. And then we can figure out that graphing inequalities is quite the same as graphing equations. So inequalities are treated as equations when it comes to graphing, except for a couple little things. Okay, except for a couple little things. There involves shading, and there involves dotted lines and solid lines. So here are a couple of differences. If we had inequality symbols, we have to figure out, well, what does that mean as far as the graphing and the shading goes? And so the first thing we have to understand is that if an inequality reads or equal to, you're going to be seeing a solid line. So if an inequality reads or equals to, you're going to have a solid line. If an inequality doesn't read or equal to, you're going to have a dotted line. So that's the first difference between inequalities and equations. We're going to have solid lines and we're going to have dotted lines, and that all depends on whether or not we're dealing with something that is or equal to or not. Now also with inequalities, we're going to be dealing with shading. So if you read something that says less than, that means the solution set is everything less than that particular line, and that means it's every ordered pair less than that line, which means we're going to have to shade down. So if our inequality symbol is less than, that means we're going to have to shade down. Okay, and similarly, if our inequality sign reads greater than, we're going to shade up. If our inequality reads greater than, we're going to shade up. And that's the difference between inequalities and equations. Everything else remains the same when it comes to graphing. So if we're looking at the example in number 1, and we're going to sketch the graph of this inequality, we approached the graphing the same way we approached equations. And if you recall from graphing equations, we had 3 different methods we could have used. We could have used a table of values. We could have used the X-intercept and Y-intercept. Or we could have used slope-intercept form. Now, slope-intercept form is going to be the most important when it comes to inequalities, because it's the slope-intercept form that will determine whether or not we're dealing with solid lines, dotted lines, shading up, shading down. Because even though this inequality right now reads less than or equal to, when we look at it in slope-intercept form, maybe it's not going to read less than or equal to. Maybe it'll change, because if you recall from inequalities, funky things happen when you divide by a negative. So let's go through each of these methods to graph, in case we forgot. So for those of you that like to deal with a table of values, we remember that we pick values for x, 2 positive values, 2 negative values, and we plug in the x value and see what we get back for y. So we have negative 2 times x minus 5y. And again, we treat it like an equal sign. And then we solve for y. Okay, so we substitute negative 2 times negative 2, positive 4. So positive 4 minus 5y equal to 15. Subtract 4 and then divide by negative 5, we get negative 11 over 5. So if we plug in negative 2 for x, we get negative 11 over 5 for y. Then we do the same thing for negative 1. So So if we're graphing using a table of values, we have to do some substituting, some number crunching, and some solving. -2 times -1 is +2. So we have +2 minus 5y is equal to 15. Subtract 2, divide by -5. And then we get -13 over 5. Same thing with 0. Plug in 0. We get -3. Or -15 over 5. Then you can see a pattern. -17 over 5 and -19 over 5. So you complete your table of values by plugging in for x, finding out what we're going to get for y. And then you have a series of ordered pairs that you can then throw on a graph. For the intercepts, when we find the x-intercept, we remember the x-intercept is when y is equal to 0. So if we had our equation, we have -2x minus 5y. But remember, the x-intercept is when y is equal to 0. And we treat it like an equation. And so to find the x-intercept, we substitute for y for 0, solve for x. We have x equal to -15 over 2 when y is 0. So we found our x-intercept. We do the same thing for the y-intercept. So for the y-intercept, again, substituting. But this time, the y-intercept is when x equals 0. So the y-intercept is when x equals 0. We treat it like an equation, and we find out that y is going to be equal to -3. So when x is 0, y is -3. We have our two intercepts, the x-intercept, the y-intercept. We can throw those on a graph, and we can graph it that way. And the last way to graph it, and again, I prefer this way for inequalities because it'll tell you more. So I'm going to this time leave the inequality symbol and show you what I'm talking about. So this time I'm going to leave the inequality symbol to find out what it will look like in slope-intercept form. The first thing I do is add 2x to both sides. And when I add 2x to both sides, I have -5y is less than or equal to 2x plus 15. And the next thing I'm going to do is divide everything by -5. And then you may see a little snag occurring. Since I'm dividing everything by -5, what will that do to the inequality symbol? Uh-oh, it changes directions. Okay, we just divided everything by a negative. The inequality symbol changes directions, and that has now just revealed everything about the new notes. That has just revealed everything we're going to need to know about the shading for the new notes because we just did that. So that's one of the reasons why it's important to at least know a little bit about slope-intercept form so you can then fix the graph and figure out what's going to happen. So we have our slope-intercept form of the inequality. And it looks like this. And now we can graph from there. So I'm going to graph going backwards, and you'll see. I'm going to start with graphing in slope-intercept form. So if I'm going to graph this inequality in slope-intercept form, I make my ordered pairs, or my coordinate plane. And I begin with y equals mx plus b, begin with my b. My b is -3. That's where I'm going to begin. So I begin at -3. I'm going to move, right, mx, I'm going to move -2 over 5. So I'm going to move down 2 and to the right 5, which puts it about here. So if I'm graphing in slope-intercept form, that's all I have to do. Boom, that way. If I'm graphing using the x-intercept and the y-intercept, I would do it a similar manner. I have my y-intercept down here. My x-intercept is at -15 over 2, 0, which is -7.5. So -7.5, 0 is over here. -1, -2, -3, -4, -5, -6. -7 would be out here, and -7.5 would be somewhere around there. And that would be my x-intercept. And if I was graphing using only the intercepts, look at that, it would be pretty much the same line. The reason this line wouldn't look straight and the same because I hand drew the graph, but you get the point. If I was graphing using the table, I would plug in all of these coordinates, right? If x is -2, y is basically -2.2. So I'd have -2 here, -2.2 here. Look, it's going to be on the same line. -1 would be here, and +1 would be here. It would pretty much be the same line. So no matter which way you're graphing it, you are still drawing the same picture of the line. Now, before we start going line crazy, we have to refer to our notes. if our equation is reading y is greater than or equal to, before we start drawing a line, we have to make sure, am I drawing a solid line or a dotted line? Since it's or equal to, we are making a solid line. So we can draw a solid line through all our points, no matter which way we made our points. And now we have to worry about shading. Okay, are we going to shade up? Are we going to shade down? So since we're reading y is greater than, we will be shading up. It's every ordered pair greater than this line. So it's every ordered pair greater than this line. So we will shade up from the line. And as we talked about for graphing equations, remember what the graph represents. The graph represents the set of all ordered pairs that would make that equation true. Well, this graph is the set of all ordered pairs that would make this inequality true. And just like inequalities can last forever, like x is greater than 2, that lasts forever. There's infinite numbers that are greater than 2. An inequality has an infinite number of ordered pairs that make this true. What are all those ordered pairs? Everything you see in the shaded region would represent an ordered pair that makes this inequality true. So it's not only being able to graph it mechanically. Remember the questions I'm asking a few things. You've got to give me an example of an ordered pair that's in the solution set. Give me an ordered pair that's not in the solution set. And does an ordered pair on the line fit in the solution set, yes or no? So we have to look at our graph and then answer those questions. What is an example of an ordered pair in the solution set? Any ordered pair that fits into that shaded region. There is infinite number of correct answers you can give. You can pick something on the axis, like here at 3, 0, or 0, 4, or 0, 5. Me personally, I like to look at the origin first. So what's an example of an ordered pair in the solution set? Good old origin. Then another question I'm asking, just to make sure you know what you're doing, what's an example of an ordered pair not in the solution set? And again, there's an infinite number of ordered pairs that aren't in the solution set. So you can give me any ordered pair that doesn't work. And again, I like to stick with stuff that's either the origin or on an axis. So a point like right here, 0, -7. That is not in the solution set. 0, -7 is down here. That's not in the shaded region. That's not in the solution set. So an example of something that's in the solution set, an example of something that's not in the solution set. What about the question, is an ordered pair on the line in the solution set? And since our line is a solid line, the answer to that question is no. An ordered pair the answer to that question is yes. Holy cow, I made a mistake. That'll learn you. So the answer to the question, since this is a solid line, is an ordered pair on that line in the solution? Absolutely. It's on the line. If it was a dotted line, then it would be no. So I made a little boo-boo there. We can overcome that. And that is how we can answer the first question. Sketch the graph of this inequality. Either use a table of values, x-intercept, y-intercept, or slope-intercept form. Example of an ordered pair in the solution, not in the solution, or is an ordered pair on the line in the solution set. So what about the second question, dealing with inequalities? I give you a graph, and you have to tell me, hey, is this graph part of the solution set? Well, we have to remember about absolute value graphs. Hopefully that's the first thing you see about this graph, that it's an absolute value graph. It's a V. And so we have to refresh our memory on absolute value graphs. And we have to remember standard form. So if you remember vertex form, not standard form, vertex form of an absolute value graph. And we have to remember everything that vertex form of an absolute value graph gives us. Okay, so this is from graphing absolute value functions. What does all this stuff mean? If we recall, the A tells us whether or not the graph opens up or down. And it also tells us the slope, That's what the number out in front gives us. The h and the k come together to give us the vertex of the graph. So the h and the k come together to give us the vertex of the graph. The a tells us whether or not the graph opens up or opens down. So we have to remember all that information from absolute value graphing. And now we look at our graph. So we can start talking about a few things. When we look at this graph, and we know it's an absolute value graph, let's look at the shaded region first. The shaded region is basically everything from the vertex up. Everything from the vertex up. So this graph is actually shaded up. And the line itself is dotted. Since the line itself is dotted and the absolute value is shading up, we can already tell that this inequality is going to be y is greater than something. Since we're shading up and it's a dotted line, y is greater than something. Okay, so we're shading up, dotted line, y is greater than something. Now, what about the a? Remember what the a tells us. The a tells us if the graph opens up or opens down and what the slope is. When we look at our graph, we can see that it's opening down. We can see that it's opening down. So the a is going to be negative. Negative what? Well, that's where the slope comes in. We have a point here and a point here. We can tell the slope. Slope is rise over run. So we're going down 1, 2, 3, right 1, down 3, right 1. That's a slope of negative 3. So you know what we know about the a? The a is negative 3. So we look at our vertex form. You know what we know about the a? The a is negative 3. And then we have our absolute value. We have the x. We also have the minus. Now we look at our vertex. Our vertex is negative 2, 3. That means h is negative 2. K is 3. Let's talk about the h real quick because that's going to be kind of tricky. The h is negative 2. Here's our equation. Remember, we have x minus, but the h is negative 2. Plug it in like you see it, and that will solve some problems. So the h is negative 2. It looks like that. We'll clean it up in a second. The rest of vertex form has a plus, and then we look at the k. Back to the graph. Here the k in the vertex was 3. So in the equation, k is 3. And we have our crazy looking absolute value vertex form equation. All we need to do now is clean it up. So we have y is greater than, the negative 3 stays the same. It's the x minus negative 2 bit that looks all funky. We're going to clean that up. And then we have the plus 3 there. And that is the equation, or the inequality of that graph we saw. It's a dotted line. It's shading up. The a is negative 3. It's opening down with a slope of negative 3. The vertex is at negative 2, positive 3. We can tell this by looking here, and it reflects what we saw in our graph. And that is how we write the inequality based on graphing. We can look at the graphs and work backwards. And that's everything that we need to know now for linear style inequalities. Thank you.